All right, well, allow me to introduce you and then I'll let you crack on. All right, so now we have Guido Bacciagaluppi. Sorry if I've murdered your name there.
No worries.
And he's going to talk to us about Bell inequality violation and relativity of pre and post selection. All right, take it away.
Thank you very much. So it's so good to see, at least virtually, so many good friends and be able to have a conference. I do miss these kind of things. So this is joint work with Ronnie Hermens. Ronnie is also here in the audience now, so he can jump in if I say something stupid. Right. So the talk will have basically three main sections. The sort of biggest one is sort of theoretical, short experimental interlude, and then we'll go on to talk about the significance of what we think might be the significance of the results, and we're most interested in feedback on the last two parts. Right. What is this about? Violations of Bell inequalities due to post-selection. This is something that was pointed out already by Oliver Cohen about 20 years ago. The idea that you can start with some pairs of particles in mixtures of up and down spins along certain directions. And then you can make certain measurements on these pairs, entangling measurements, and then post-selecting on the results of these measurements, while initially you had an ensemble in which there was no violation of the Bell inequalities, you can get ensembles in which there is a violation of the Bell inequalities. And here's how the proof goes. The entangling measurement we are going to think about is a Bell measurement, a measurement of the four maximally entangled states of two spin 1/2 particles, and the sort of initial ensemble that does not violate the Bell inequalities is just a 50-50. Sorry, it's a mixture. So we've got two particles prepared by Alice and Bob, and Alice has measured spin along one direction, alpha-1, or another direction, alpha-2, and prepared 50-50 mixtures of up and down in one direction or another. Same with Bob. He's prepared 50-50 mixtures of spins up and down in one direction, beta-1, or another direction, beta-2. And their spins get paired randomly. And then on these pairs, we have the Bell measurements performed by Vicky. Right. Now, this table, these are the transition probabilities between the Bell states and the states up, down, down, up, down, down, up in two spin directions. So if we take a Bell state and perform measurements of spin along these directions, these are the probabilities for the results. And with appropriate choice of directions, we're going to violate the Bell inequalities. In fact, with appropriate choice of directions, whichever Bell state we start with, we're going to violate at least one Bell inequality. But also, the transition probabilities are symmetric. So if we start off in this product state and perform a Bell measurement, these are the probabilities to get the four Bell states. Well, if we start in an equal mixture of these four and measure spin along these two directions, we're going to get a completely mixed ensemble of ups and downs, but it's the mixture of four sub-ensembles which all violate the Bell inequalities, and vice versa. If we start in a uniform mixture of these four and perform the four Bell measurements, it follows that we'll get an equal mixture of these four, but we'll have four sub-ensembles, which are the same four sub-ensembles had we done the measurements in the reverse order. So in these four sub-ensembles, we are violating the Bell inequalities. So concretely, let's choose these directions, and then we start off in this uniform mixture of these product states. Vicky performs the Bell measurement, and then in the four sub-ensembles corresponding to the four results of the Bell measurement, we have violation, maximal violation of these two Bell inequalities, the Bell correlator S1 and the Bell correlator S2. If we take these, we get violations of the Bell inequalities. So that's a well-known result by now, proven by Oliver Cohen in 1999. And soon afterwards, Asher Perez proposed a nice experiment to see this, which he called the delayed choice entanglement swapping, which is the one here on the right-hand side. I'll start first with the one on the left-hand side. What this is supposed to represent is, we've got two pairs of entangled particles, and then Vicky performs an entanglement swapping. That has as a consequence that these two particles now are entangled, and then Alice and Bob can perform a usual EPR Bell measurement on these entangled particles. And now what Perez proposed was to wait with entanglement swapping until later. So we are switching the order of the measurements, and the intuitive way of thinking about what's happening is we've got these two pairs of entangled particles, and then Alice and Bob perform their measurements, collapse Vicky's particles at a distance. So now we've got a completely mixed state of two qubits, and then Vicky performs the Bell measurement and post-selects and gets the same results as with an EPR Bell measurement where the entanglement had been produced by entanglement swapping. And so this is the experiment proposed by Perez, and it was performed by Ma et al. In 2012. And this experiment is just a standard EPR Bell experiment, but where we prepared the entangled pairs using entanglement swapping. It's very similar to the Hinson et al. Loophole-free EPR Bell experiment, not exactly, because in the Hinson et al. Experiment, I should have drawn these as sort of big ovals. The settings, the directions in which the spins were measured were determined at space-like separation from the entanglement swapping, while the measurement was completed in the future light cone of the entanglement swapping. So this is not exactly the Hinson et al. This is preparing an entangled state via entanglement swapping and then doing an EPR Bell measurement. And this is Peres's experiment, delayed choice entanglement swapping. We prepare this maximally mixed state at a distance by performing measurements on the distant particles in Alice's and Bob's lab, and then Vicky performs the Bell measurement and post-selects. Right. Now, in the case of the standard Bell EPR Bell experiments, we know that the violations of the Bell inequalities can't be reproduced using local hidden variables, and when we do experiments, to test that, the experiments are carefully designed to avoid any loopholes, avoid any way that there might, after all, be a local hidden mechanism that explains why the Bell inequalities are violated. But that was not the point of this experiment. What we are asking now is, is there possibility of some local hidden mechanism in this experiment that might explain the violation of the Bell inequalities? And if there is, how can we rule that out? So, here we go. So, I'm going, well, the answer to the first question is yes, there is the possibility of a local hidden mechanism. And I'm going to illustrate what that mechanism is using a purely classical example. So here's the classical example. Alice and Bob are just flipping coins. And Alice has the choice of flipping either a $quarter or 100 yen piece. Bob has the choice of flipping either 50 euro cent or British 10p. And each experiment is binary, heads or tails as outcomes. And we've got a certain preparation of these coins. We're just sending fair coins to Alice and Bob. And if you want to see causal diagram of what's happening, it's all very simple and straightforward. Now, in this situation, if we've got fair coins, clearly the probability that if Alice and Bob flip, say, dollars and euros, they get the same result is 1/2, or the probability that they get different results is 1/2. So we've got no correlations, and the same, whatever pairs of coins Alice and Bob flip. So in particular, the Bell correlator S1 is 0, and the coins satisfy the Bell inequalities. And the same for all other Bell correlators. This was for the case of fair coins and uncorrelated ones. It's true also for biased coins, and if we have classical correlations to start with. This should all of this should be obvious and easy. And now comes the interesting bit. Suppose that Vicky now performs a post-selection on these coins. So Alice and Bob have prepared these coins, and they send them to to Vicky, and Vicky now performs a post-selection based on classical information. These are classical systems. There are no entangling measurements. Just based on classical information, Vicky performs post-selection and subdivides all these coins into 4 sub-ensembles and claim Vicky can do that in such a way as to violate the Bell inequalities in each of these 4 sub-ensembles. How does that work? Here is the explicit construction of 4 such sub-ensembles. So we'll take so Vicky takes half of the pairs with where we've got the same result in case Alice and Bob have flipped dollars and euros. Vicky takes half of the pairs with the same result where dollars and pounds had been flipped. Half of the pairs with the same result with yens and euros, and half of the pairs with a different result with yens and pounds. And this is the first sub-ensemble. Similarly, second half ensemble, sub-ensemble, it takes half of the pairs with, so the other half of the pairs in which Alice and Bob got the same result with dollars and euros, the other half of the pairs with the same result for dollars and pounds, and then half of the pairs in which they got different results for yens and euros, and half of the pairs in which they got the same results for yens and pounds, and so on. First sub-ensemble, second half ensemble, third sub-ensemble, fourth half sub-ensemble, and these are all the pairs of coins now. This is an exhaustive subdivision into 4 sub-ensembles. And now, if you look at how the sub-ensembles have been constructed, here we've got a sub-ensemble with perfect correlations for 3 kinds, kinds of choices, and perfect anti-correlations for the 4th. And all of these sub-ensembles are like that. We've got either perfect correlations for 3 choices and perfect anti-correlations for 1, or perfect anti-correlations for 3 choices and perfect correlations for 1. That means that if we compute the Bell correlators, we get super quantum violations. We get S1 equals 4, S2 equals 4, S2 equals minus 4, and S1 equals minus 4, respectively, in these 4 sub-ensembles. So we had a bunch of coins which had been flipped, producing heads or tails, and of course, the initial ensemble did not violate any Bell inequalities, but here is an explicit procedure to select 4 sub-ensembles in which not only do we have violation of the Bell inequalities, we in fact have super quantum violation of the Bell inequalities. I hope that was straightforward enough. I mean, it is straightforward. It's a very simple procedure that Vicky can follow, and Vicky can subdivide the given pairs of coins into these 4 sub-ensembles. Now, what Vicky used, what was crucial, was information, was classical information. It was information about Alice's and Bob's settings, which coins they had flipped, and about their outcomes. The selection was based on taking, here are the pairs in which Alice and Bob have flipped dollars and euros, and they got the same result. So it's classical information about the settings and about the outcomes. If Vicky has this information, Vicky can perform this protocol and subselect the ensembles that violate the Bell inequalities. Now, in the quantum case, the way Vicky violates the Bell inequalities is completely different. The information about Alice's settings and Bob's settings and their outcomes are not contained in the quantum states that Vicky gets. Vicky just gets a maximally mixed state of 2 qubits. This maximally mixed state has been prepared in a certain way. Alice and Bob have performed certain measurements, along one spin direction or another, one spin direction or another, and then they've just collected all the results to get these mixed states, and they've sent them to Vicky. But the quantum states don't carry themselves the information about how they were prepared. So this information that Vicky uses in the case of the coins to violate the Bell inequalities is not what Vicky uses in the quantum case, and in fact it's not information that's contained in the quantum states of the spins that Vicky gets from Alice and Bob. Question: can we distinguish experimentally this quantum case from the idea that, there might be a hidden mechanism? So information about the settings and the outcomes is not contained in the quantum states of these qubits, but there might be some hidden variables, that encode this extra information, and maybe these hidden variables are determining the result of Vicky's entangling measurement, so that Vicky thinks that this is a sort of genuine quantum phenomenon with no classical explanation, but there is actually a hidden mechanism that is exploiting this simple strategy of post-selection based on classical information, hidden classical information. Can we distinguish these two cases? Can we rule out that in an experiment with an entangling measurement on pairs of qubits, can we rule out the possibility of a hidden mechanism of this kind? And the answer is yes, but not in experiments that have been done already. So in particular, if we think of the Ma et al. Experiment, Alice and Bob are preparing the mixed state in the past light cone of Vicky's entangling measurement. It was over here. So the information about their settings and their outcomes, even though it is not encoded in the quantum state of the qubit pairs, is in principle available at Vicky's site. So there might be a hidden mechanism that is in fact determining the results of Vicky's entangling measurement. If we want to rule out this possibility, we have to remove the possibility of causal links between the choice of settings and the outcomes and Vicky's measurements. And the way to do that is straightforward. Instead of having Vicky's entangling measurement in the future light cone of Alice and Bob's measurements, as in the Ma et al. Experiment, we should delay the entanglement swapping, but not for so long. We should wait less. We should have Alice and Bob's measurements be at space-like separation from Vicky's entangling measurement. In that case, indeed, the information about their settings and their outcomes is in principle unavailable at Vicky's site. And such a hidden mechanism as we have described cannot explain the violation of the Bell inequalities. By the way, if one does this experiment, one should, of course, also take care that Alice's measurements and Bob's measurements are space-like separation from each other to avoid the standard locality loopholes for Bell inequality violation. But this is what we propose. We propose to have an entangling measurement and the spin measurements, all at mutual space-like separation. And right, so that was our theoretical analysis of what's happening, of what might be happening, and this was a short experimental interlude. What one should do to rule out a hidden classical mechanism, and please give us feedback on this experiment. What I want to conclude with now is an analysis of sort of conceptually what this is telling us, and the basis of this is the following realization. The experiment, in which we've got Alice and Bob measuring spins and Vicky performing the entangling measurement, is interpretable in two different ways. It's indeed a variant of the Ma et al. Experiment. Alice and Bob are preparing this uncorrelated, completely mixed state of two qubits, and Vicky makes a Bell measurement and post-selects on the basis of that. Or we can interpret it as a sort of good old preparation of a Bell state using entanglement swapping, and then Alice and Bob perform a standard EPR Bell experiment. since these measurements are all at mutually at space-like separation, the time ordering is arbitrary. So we can interpret this as Vicky is preparing an entangled state on which Alice and Bob perform the EPR Bell experiment, or Alice and Bob are collapsing at a distance, the states of Vicky's particles, and Vicky has a completely mixed state and performs the entangling measurement on. Now, Abner Shimoni, in a beautiful paper of 1986, Events and Processes in the Quantum World, was complaining, that on the one hand, quantum events and their probabilities are relativistically invariant, but the theoretical process of evolution of quantum states, when we perform a measurement, is not relativistically invariant. Nice quotation here. The two accounts of processes from initial to final sets of events are in disaccord. But it is important to note that the process is a theoretical construction. Now, the thesis of peaceful coexistence, one of Abner's favorite phrases, presupposes a conceptually coherent reconciliation of the descriptions from the standpoints of the frames sigma and sigma prime. And even more desirable, in the spirit of the geometrical formulation of a space-time theory, would be a coordinate-free account. Now, these remarks by Abner, sorry about the noise from the street, were in the context of EPR. Standard setup, Alice and Bob have, say, a singlet state. They measure spin along two different directions, and suppose the final result is Alice got spin up in X direction, Bob got spin down in Y direction. And if we describe this in two different frames, in one of which Alice measures first, in the other one, in the other of which Bob measures first, then the state between the two measurements in the first frame is the one that Alice has produced by collapsing the state of both particles through her measurement. So it's up-down in X direction. In the other frame, in which Bob measures first, he's measured along Y, so he's collapsed the state onto up-down in Y direction. So the two frames, the descriptions of the quantum processes, how the quantum state evolves from the initial singlet state to the final state up in X, down in Y. This process is frame dependent. But the initial state, the final state, the measurement results, their probabilities, all of these are Lorentz invariant. That's what Abner means here. The processes are frame dependent. The account in terms of processes is frame dependent, but in terms of the quantum events, in this case, measurement events and their probabilities, that's an invariant description. And Wayne, who's going to talk after lunch, has coined a lovely phrase for this, the relativity of entanglement. Whether or not the two particles are entangled when Alice performs her measurement is frame dependent. If in a frame in which Bob has already performed his measurement, they are disentangled. In a frame in which she performs the measurement first, they are entangled. But at least what we've got here when we tell the story in terms of who collapses the state is the same kind of physical process. Which which measurement is collapsing the state depends on the frame of reference, but the explanation for what's happening is the same kind of explanation, irrespective of the frame we choose. The first measurement to happen collapses the state of both particles, and that explains why we get the correlations that we get between the results of the two measurements. We've got a unified explanation. I mean, it's the type of explanation is frame independent. The details of the process are frame dependent, but the kind of process is the same. We've got this explanation that the first measurement collapses the state of both particles. That explains why when the second measurement takes place, the results are correlated in a certain way. Now, in the experiment that we're proposing, we've got two different kinds of explanations for one and the same violation of the Bell inequalities. And we suggest this is really the sort of striking twist in the scenario that we're looking at. And if we have a Hinson et al. Type experiment, we've got Vicky preparing an entangled state and Alice and Bob doing a standard EPR Bell measurement, that's one kind of explanation of the violations. We are violating the Bell inequalities because Alice and Bob are making their measurements on a pair of entangled particles, and these are non-local correlations on a pair of entangled particles. But if we interpret it as a variant on the Ma et al. Experiment, okay, there's some non-locality involved. That's Alice and Bob preparing at a distance, Vicky's particles, but that's not non-locality that violates the Bell inequalities. It's just perfect correlations. And the violation of the Bell inequalities instead comes about because Vicky is performing this entangling measurement on this pair of particles. That's a weird quantum thing, but it's local. And then performing a post-selection based on that result. So we have one and the same phenomenon. We've got one experiment in which we have violation of the Bell inequalities, and we have two very different explanations, depending on the foliation we choose. In one case, we've got, here's in this foliation, when Alice and Bob perform their measurements first, we get a dynamical explanation of what's happening, an evolution of the quantum state that leads to an explanation in terms of post-selecting on the basis of the results of a Bell measurement over here. And in this case, in which Vicky's measurement is performed first, in this foliation, we have the same violation of the Bell inequalities in the same experiment, but it's explained in a completely different way. The explanation is Vicky has prepared an entangled state, and then we have sort of standard non-local violation of the Bell inequalities when Alice and Bob perform their measurements. But we argue, because this is just a choice of foliation, a choice of description of one of the same physics, the distinction between these two explanations is meaningless. Our conclusion, and I'm being provocative here, and we are not the first people to suggest this. I mean, ever since, at least ever since the early 80s, Aharonov and Albert, have said similar things in the early 80s, and of course, Shimoni, Mervold, there is so the suggestion that there's something non-fundamental about the evolution of the quantum state, we suggest that this is a case in which that becomes much more painfully obvious. These two different dynamical explanations in terms of the evolution of the quantum state can't be fundamental explanations. Just like in 1905, first paragraph of Einstein's paper on relativity, two frame-dependent explanations of electromagnetic induction, depending on whether it's the magnet that moves or the conductor that moves. These can't be fundamental explanations. What's fundamental are just the correlations between three measurements of mutually commuting quantities, and then conditionalizing on the results of Bicky's measurement. And we would like to suggest these dynamical explanations in terms of the collapse of the quantum state, if they are not fundamental in the case in which the three measurements are at space-like separation, are probably not fundamental either in the case of time-like separated measurements. The fundamental explanation should be one in terms of just the correlations between three mutually compatible measurements. So the Schrödingerian, quasi-Schrödingerian picture of a quantum state evolving is indeed just a theoretical construct. It's a theoretical process, a process that's a theoretical construction using Abner's words. And what is fundamental, and Carlo, if he's there today, will be glad to hear that. Is this sort of Heisenbergian picture of these sparse quantum events. And here are a few references. We've got the paper or draft on the archive. Thank you very much.
Okay, thank you. If we could applaud the speaker in the usual way. I think everyone appreciated that, and we have some questions. So first up, let's go to Aurélien. You're first, I think.
So thank you very much for the. You can hear me? Yes, it's on. Thank you very much for the very interesting talk. This topic is very fascinating about Lorentz invariance and all these things. Is a very central issue for understanding quantum mechanics. Probably it's I think this kind of issues can be clarified probably if you watch the picture of Bohmian mechanics, even though there are not so many papers on this issue. But if you watch, for example, already the book of Bowman Eiley in 1992, I think, he discussed a bit the problem of what happens if you change foliation of space-time, and then you realize that the dynamical structure, the trajectories that you compute with Bowman mechanics are completely modified, change. And they are, after that, there are also very interesting paper by the group of Dur and Goldstein and Zengi. They made a very nice picture with what they call the Bohm-Dirac model, and using the Dirac equation, and they observed that the choice of the foliation is really modifying the trajectory, and it seems that you are obtaining a completely different picture in both cases, but at the end, if you assume the bound rules, if you assume what they call a quantum equilibrium, so the idea that you have a bound rules is valid in a general fashion, then you can never find contradiction between the different point of view. Only if you assume that you have non-equilibrium, like Valentini would say, then you can see difference and you can see discrepancies. So I would say that it's because you assume bound rules and then no signaling that you have no possibility to see any contradiction. So this is the fundamental issue. Here is no signaling, so bound rules. Yeah, it's and I wrote recently a review paper on that topic. I can put the link here if you want. But, yeah.
Thank you. Yes, no, I completely agree. I mean, on a different occasion, I might have given a talk on pilot wave theory. Yes, of course, in pilot wave theory, there's a perfectly consistent way of describing what's happening, and yeah, I mean, there will be a preferred frame also, and then there will be a definite story to be told, about what's happening, and an explanation for why the Bell inequalities are violated, and it will probably be different, depending on. I mean, there will be some cases in which objectively, Vicky's measurement, happens first, and then there will be one well-defined Bohmian explanation. There will be other cases in which Alice and Bob's measurements happen first. There will be another perfectly well-defined Bohmian explanation. I completely agree. I mean, the context, of today's talk is more, well, let's think of relativistic collapse theories, and how should we make sense of those, and so on. And within that context, what we are suggesting is, well, maybe I mean, to sort of translate into primitive ontology terms, we're saying maybe we should adopt a flash ontology, rather than one based on rather than a wave function ontology or mass density ontology. That's a context in which I was talking today. But, I agree completely with what you've said.
And it touches also the problem of retrocausality in retrodiction, so it's very, very fascinating.
Thanks.
Okay, next we have a question from Jeremy.
Oh, thank you very much, Richard. Thanks, Guido, for a wonderful talk. I would like to pick up on what you were just saying. It's fortuitous, because my question was about your last slide about the Schrödinger and the Heisenberg. This is new to me, and so it's a bit of a strain on the brain, but I just want to clarify. Nothing you say is against the orthodox elementary equivalence between Schrödinger and Heisenberg pictures of evolution, where putting the time dependence on the state as against the quantities, but you're rather suggesting that whichever of those elementary choices one makes, the idea of the quantum state as the reality is misleading.
Yes, I mean, it's not a choice between Schrödinger picture and Heisenberg picture in terms of the formalism.
No.
Although, so
normally those are reconciled even in dynamical collapse theories by careful verbal formulation of with respect to which sectors of space-time one is considering a unitary or non-unitary evolution.
Yes, and I mean, and yeah, a very, very easy way of picturing yeah, no, never mind. Yeah, so it's not about showing you a picture and Heisenberg picture. Yeah, it's about what the natural ontology is going to be. So if we think that somehow we fundamentally have quantum states which are which will have to be hypersurface dependent. Here we've got hypersurface dependent quantum states evolving, as the hypersurfaces get pushed up. That is just mathematical representation of something that's not fundamental, because it just gives us the same kind of things like explanations of electromagnetic effects based on electric fields versus based on magnetic fields. These are sort of useful, and they're certainly they're certainly good explanations. Frame dependent explanations are perfectly good explanations. Length contraction is a dynamical effect in a frame, and so on and so forth. But one might want to say, look, let's really focus on the invariant stuff. And we think this example brings that out very, very vividly, because depending on the choice of foliation, we seem to have different mechanisms operating to explain one and the same phenomenon.
Thank you.
Okay, and after that we have a question from Chris.
Thanks, Guido. I'm delighted that you and Ronnie have looked at the post-selection in the Henson experiment case, and I thoroughly concur with your approach and analysis. David Glick and I looked at the Marr experiment and the Perez delayed choice challenge a few years ago, and Hugh Price said to us after that, well, what about the Henson experiment? And I said, I don't know, I've not looked at it. So you've done that now. And so now we know what the answer is, which is good. With
Ken Wharton, I have just put a paper on the archive in which they look at that.
Good. The interesting thing about the Perez challenge, also the Healy challenge from delayed choice, is that you can see it as a challenge to realists, or those who want to be realist about entanglement, to say that there's a genuine entanglement relation in the world. And Perez is trying to say, look how silly you're going to be if you believe that entanglement is a genuine relation in the world, because you're going to have to believe in action to distance into the past. The post-selection, the actions done in the future make it the case or don't make it the case that there was entanglement in the past, and that is ridiculous. And so the thrust of our analysis, and we can see it in your analysis too, is to show that that's completely mistaken, because obviously if you're using post-selection, you don't need entanglement to violate a Bell inequality. Whoever would have thought you did? It's just crazy. But there's still a bit of a challenge. And it is, okay, what's doing the explanatory work here? And that's something you were getting at in your last slide, and you're saying, well, maybe we need a picture, maybe the Heisenberg picture, but that's another story, to give us an explanation here. I had a different kind of realist defense, which was to say that there is a realist explanation for the fact that it looks as if you've got entanglement in the past, as it were, being created in the past. And it's really the case that there's a real symmetry in your theory, and there's a real time symmetry in your theory. And it's the time symmetry of preparation and measurement. If you prepare in a given state psi, measure and project onto it to get a particular phi out, you get the same probability as doing that the reverse way round.
Mm-hmm.
You can see all of this as just being instantiations of that. So the unifying realist defense, whether you're a collapser or not a collapser, is to point to this real fact about real time asymmetry. That's the lesson I take. And I don't think you should take the Heisenberg view. You should just say that believe in the Schrödinger case, but don't believe in collapse.
Okay. Go ahead and respond.
You might need to. You might need to unwrap that very last remark again. But yeah, I completely agree. The symmetry, the time symmetry of the transition probabilities is the key to understanding the violation of the Bell inequalities with post-selection. And yes, there is no need to think in terms of well, I mean, there really was entanglement. There was hidden entanglement. There was counterfactual entanglement. In the past. That's the way Oliver Cohen puts it in his original paper. But that's, yeah, I think that's not necessary. Just the symmetry of the transition probabilities, is enough to understand what's going on.
Okay, so that brings us to, I think, our final question from Gerard.
Sorry. Yes. Sorry.
Yes.
Thanks. That was a nice talk. My question refers to your diagram where you have deformed foliations. I didn't quite understand how that would make sense in flat space-time.
Flat space. These are just. Let me just move. I'm still sharing, so I can move back to that slide.
Accelerating observers.
So I mean, this is in Minkowski space-time, and just looking at different space-like hypersurfaces, so foliating different foliations of Minkowski space-time into space-like hypersurfaces. So I mean, when people do sort of relativistic collapse theories, they use a kind of Tomonaga-Schwinger picture. So we've got foliations into arbitrary space-like hypersurfaces, and the quantum state is defined on is relativized to hypersurfaces, and then because it's a collapse theory, some funny things happen during the evolution, which don't happen in Tomonaga-Schwinger quantum field theory. But that's what it is. Minkowski space-time and arbitrary foliations into hypersurface.
Right. Okay. But it looks more like curved space-time to me, in which case all the probabilities are not correct.
Look, I mean, if you just want good old Lorentz frames, then all you need to do is change the geometry. Have Alice, Bob, and Vicky in a triangle.
I see what you're saying. Okay, fine. Okay, so you just move Alice slightly forward. You just move Alice and Bob slightly forward to Vicky in A and slightly behind.
Yeah.
Yeah. Okay, fine. Good.
So I misled you before. There is a further question from Kaslav. So do you want to go ahead?
Yeah, thanks. Thanks, Guido, for the talk. I just have a very general comment on post-selection. And I just maybe it clarifies also for other people that post-selection is doesn't not open a loophole in general. and experimentalists actually post-select the data all the time, even when they prepare entangled states. Usually they have maybe like one particle which is a trigger, and then they select this trigger, so they post-select data. This what opens a loophole such that local realistic theory or local hidden variable theory can violate Bell's inequality if you do this post-selection or selection dependent on the choice of the measurement setting. But if you do it this post-selection independent of the measurement choice, you can do it, and local hidden variable cannot lead to violation of Bell's inequalities. So there are, in a sense, good and bad post-selections. And so if you just post-select on an outcome, it doesn't matter, you can do that. If this is not correlated with anything like measurement settings. That's a general comment, and yeah.
Yeah, no, yes, I think you're right. In fact, at one point, Ronnie and I were we're trying to look at the details and prove a general theorem that if you post-select on outcomes and not on settings, then you can't violate the Bell inequalities. I don't know. I mean, if you actually have we only had partial results. If you actually have a proof, please let me know. But yeah, I think that's I think that's right. But yeah, I mean, here we don't know anything. So we're talking about a loophole in the Ma et al. Experiment, and yeah, I mean, there. I mean, not knowing what the hidden mechanism is, I mean, this is totally. I mean, we don't believe in such a hidden mechanism. We don't really think we need an experiment to rule it out from that point of view. But if any hidden mechanism might be conceivable, then it could be a hidden mechanism that exploits also information about the settings, because those are in the past light cone of Vicky's measurement in the Ma et al. Experiment. So in that sense, a loophole, a hidden mechanism that utilizes this as a loophole is conceivable. Yeah, maybe it's not very believable anyway. But in order to rule that out completely, we would have to have space-like separation. That's the point.
Okay, well, if there are no further questions, can we thank our speaker one more time?
Thank you.
And thanks very much for the talk.
Yeah, no, let's
So at this point, we're coming up to lunch. So we will be returning at 2:30 CET, which is an hour and a half from the hour upcoming, if that makes any sense to you. But yeah, 2:30 CET, where you'll have a different chair, Hippolyte, and we'll continue the session. I think Christian might correct me that this is all staying on, so if people want to chat, they can. If that's not true at all, speak now.
I can leave it on for a while if you want to chat.
Okay, perfect. Right. Well, with that, thanks everyone, and thanks for attending this morning.
Thank you, Richard.
Thank you, Richard.
Thank you, Guido.